Just before he died, Nicholas Copernicus published his revolutionary work detailing how you could calculate the distance between the planets and the Sun. While finding the distance between Venus and the Sun and Mercury and the Sun is relatively straightforward, the superior planets like Mars, Jupiter, and Saturn were a little more challenging. This video is going to focus on how he calculated the distance between Mars and the Sun, or the Mars-Sun distance. Now, he obviously couldn't measure that all on his own, but he could measure that in terms of the Earth-Sun distance, what he termed the astronomical unit, or 1 AU. Notice here how he has a right triangle. Normally we could solve this, but there's a problem. This angle here, you'd have to be living on Mars in order to view the angle between the Sun and the Earth. You'd have to be living on the Sun to measure this angle directly, which you also can't do. But he had a trick up his sleeve in order to figure out this angle right here. Copernicus knew that earlier in the year, Mars was in opposition. Notice how Mars is basically in the opposite side of the sky as the Sun. Then over time, they moved to this new position that he called quadrature, and it took 97 days between these two events. So notice now that Mars has moved that red angle, and we have the gray angle that we're looking for. Notice if I were to add those two angles together, I would actually get the larger angle, the blue angle, that Earth has moved through. If I rearrange this equation, I see that the gray angle is equal to the blue angle minus the red angle. So I need to take the days that these planets have spent traveling through space and convert them into degrees. Thankfully, I know that the Earth travels around the Sun, and it takes 365 days to do that. Assuming, like Copernicus did, that it was a perfect circle, which it's not, that would be 360 degrees in 365 days. So, if Earth had been traveling for only 97 days, I take 97 divided by 365, multiply it by the 360 degrees of a circle to learn that the Earth in 97 days has traveled 95.7 degrees. Now I can do the same thing for Mars. Mars takes 687 days to orbit the Sun one time to make its 360-degree circle that Copernicus assumed it was making. Now notice that Mars, we said, has also moved 97 days. So if we take 97 days divided by the 687 days of a Martian year, multiplied by 360 degrees, we learn that Mars must have traveled 50.8 degrees. So if I take the 95.7 degrees, subtract away the 50.8 degrees, I get 44.9 degrees. That's the angle that I was hoping to find. Now I have a triangle that I can solve. Remember that we wanted to find the Mars-Sun distance, which we'll call that D, and I knew the Earth-Sun distance is 1 AU. Notice that D is the hypotenuse of my triangle, and that 1 AU is the adjacent side to the 44.9 degree angle. So remembering SOHCAHTOA, I know that I need to use the function cosine. So cosine of 44.9 degrees equals 1 AU, the adjacent side, divided by D, the hypotenuse. I can multiply both sides by D. That's going to get rid of D on the right side and leave me with D times cosine of 44.9 equals 1 AU. Now I still need to get D by itself, so I divide both sides by cosine of 44.9 to get D equals 1 AU over cosine of 44.9. I put that straight into my calculator, and I should get 1.4. The distance between Mars and the Sun is 1.4 AU. And I can do the same basic setup for any other planet that is further away than the Earth is.